This little circuit here looks a lot more complex, but it's not, and it's just illustrating a MOSFET being used as a resistor again. So what I've got here is I've got an op-amp running off plus or minus 15 volt power supplies, just here, the red wire, the blue wire. I've got it wired up with negative feedback to make it into an amplifier. I've got my input voltage, just here. Notice we're measuring in millivolts this time, so very small input voltage. My output voltage, just here, again measuring in millivolts. And I should know that for a non-inverting amplifier, which this one is, the gain equation is 1 plus RF over RI. And on my diagram, this is my RF and this is my RI. So the MOSFET's effectively behaving as a resistor. And I'm not measuring the gate source voltage this time. I'm just adjusting it. I'm not measuring it in any way. Okay, so my pink wire here is the gate voltage. My green wire here connects the MOSFETs connected from ground through the green wire to pin 2, and then through this resistor here, which is now 10K, not 1K, as in the previous part, to the output. Output's coming down to the voltmeter. Right, now, if we look at the voltage scales there, we see you've got 5 millivolts in and about 50 millivolts out, so the gain is approximately 10. So what must RI be? Well, if the gain is 10, RF over RI is 9. Okay, the feedback resistor, this one here is 10K, so this must be around about 1K, just a little bit more than. Now what happens if we change it? Well, if we make the gate source voltage smaller, this value is going to get much bigger. When this value gets much bigger, then this value gets much smaller, and the gain tends to 1. So as the gate source voltage goes down, RI tends to go up, becomes very, very large, and therefore Vout tends to become, well, what does it tend to become? When this is very, very large, this number is very small, so the gain is 1, so the output just becomes the input. Okay, so that's what they tend to become. Let's have a look at that, if we can do that. So we'll take our voltage right down, and what you can see now is that my meters aren't necessarily very accurate, they're not quite reading the same value, but the output and the input are the same. If I change the input voltage, they're pretty close to being the same. So the gain of the amplifier is pretty close to 1 as I change the input voltages around. Okay, so the amplifier's gain is 1. As the gate source voltage goes up, RI tends to go down, which is a bad thing, and therefore the gain, what's going to happen to the gain in this case? Well, when this gets to be very small, this number becomes big, so the gain tends to go up, and therefore the out tends to go up as well. Let's see if we can demonstrate that. So I'll turn my voltage back up. I'm going to turn this back down to just give me a very small input voltage, because we are amplifying it, so we don't want to have a big starting voltage. Remember, for the MOSFET to be in its resistive region, you've got to be working with pretty small voltages. Okay, you don't want anything too big, because otherwise it's in its current sink region instead. So just a bit more than nothing, though, would be quite good. There we go. So that's back to about 7 millivolts going in, 7 millivolts coming out. Let's see what happens as we turn the gate source voltage up. So not a lot to start with, as we'd expect, when we have to go up to 2 or 3 volts before anything happens. And now you see the output voltage is starting to go up, even though the input voltage isn't, which suggests the gain is changing. So there we're back to having a gain of 10, which is where we were before. Okay, and if I change the input voltage, then the output will change. If I keep going, then you see it very quickly. I have to change scales in a moment. Very quickly, my gain is so big that the amplifier is just saturated. So 7 millivolts in, 14 out. That's not amplifying, that's just saturated. The output's just the supply voltage minus 0.7. And if we go back down again, that appears to work. So that's 1,200 odd millivolts for 7 millivolts in. So that's a really, really high gain. But it doesn't work, because if I change the input very slightly, the output doesn't change in a linear way. That's not really doubled. Okay, it was 1,204, it's now 2,300. Because remember that if I've got an output voltage of 2 volts here, then this is probably now not working in the region where it's less than a volt or less than half a volt. So unless your input voltage is very small and your gain quite low and the output voltage remains relatively small, it's very easy to take this MOSFET out of its resistive region. So if we go back down a bit, turn it back down to millivolts again, and that's more reasonable. That's a gain of 4. Okay, so that would be quite nice. So if we remember our graph that we had, we had VGS. You have to watch out with these graphs what you're actually plotting. It's either VDS or VGS. VGS in this case. And, or is it? No, it's not. See, I made that mistake myself. VDS. Then what we get here is we get a curve like this. At lower gate source voltage, we get a curve like this. The resistance is higher. And at higher gate source voltage, we get a curve like this. So the resistance becomes lower. But this has to be the order of a few hundred millivolts maybe, yeah, before this starts to go wrong. Certainly less than 1 volt, which is what we had last time. Okay, so this is how my MOSFET's being used as a resistor in an amplifier. But the criteria are, you have to work at really quite small voltages, millivolts, not volts.